Welcome to our final presentation on Neuralizer, our senior capstone of spring 2021, brought to you by Case Western Reserve University. So within the past couple of decades, there's been a problem in society of fake news or misinformation meant to mislead people, or news solely for profit and not for informing readers. And unfortunately, this issue has been catalyzed by the recent 2016 elections and certain issues around the world. And of course, in a democracy, you need healthy debate. And in order to have healthy debate, there have to be a basic set of facts that both parties agree on. And with fake news, a lot of times people who constantly consume fake news, their basic facts tend to be warped. And a lot of times it's hard to discern whether you're reading fake news or how biased news source might be. And that's where our project comes in. What we've done is use artificial intelligence and machine learning in order to detect how much bias there might be in a news article, and by extent, how fake or misinforming it might be. And what we decided to do is make an easy to use website where you can plug in the URL of a news article, and we scrape the news article for the title and the body paragraph info. And then we run that through the news Neuralizer in order to see its reliability, how fake it might be or how real it might be based on that. So we define fake news as complete fabrications, satirical news, and poorly written articles. Research studies have created models with a success rate as high as 92% accuracy, and an API has already been developed to check whether an article was professionally written, but no easy-to-use website was developed. So that's where we come in, and we use these libraries and already created technology in order to get that to the normal user and normal citizen consuming news. And this high accuracy means the concept has promise, but it cannot help everyday users and be tested if they have no easy access to models, which is what we aim to do with publishing this website. So my name is Noah Friedman, and I designed the front end CSS styling and the overall hamburger website style layout.
And I'm Bertram. I also worked on the front end. I worked on the web components and their functionality.
Hi, my name is Thomas Patton, and I worked on the machine learning model, some of the research that went into selecting data sets and making some analysis of the results.
Hi, my name is Beltran. I also worked on the ML model, working on vectorization, classification, and analyzing the results.
My name is Phan. I worked on the backend for the server and also the newsfeed implementation and also the scraper implementation to send to both the ML model and front end.
So for the front end, our goal was to create basically an entry point for users to access our machine learning model easily. So we decided to make a website for that. Our tech stack was React.js and Bootstrap so that we could easily basically develop a single page application. We figured that to make fake news detection very easy, all the user had to do was input a URL, and then we would do the scraping for them. Of course, the scraper will be talked more about by Phan in the backend, but here is an example of just a fresh load of our website. You're greeted by just a quick introduction of what we do. This is where the URL can be inputted, and a manual input form if the user, for whatever reason, doesn't want to use our scraper. So if the user does decide to use the scraper, they can put in their URL. They'll press autofill, and then a new form will be loaded, and it'll have whatever we scraped from the website. So over here, we scrape the title and we scrape the article body. These are input forms, so that means the user can go ahead and check if we scrape the correct information. Our scraper isn't perfect, but it gets most of the information generally. And if they see something that they don't like, or maybe we missed something, they can always just add it themselves inside of the form. Once they press Neuralize, we will have our verdict loaded, and the user can just kind of read and make sure that whatever we judged was what they wanted to input. Of course, again, if the user doesn't want to use the scraper, the manual form's always there. We also decided that it'd be fun for the user to see what our machine learning model thought of the hot news of the day. So over here, we created a news feed of kind of pre-checked news. Over here on the left, we'll have the true articles, and on the right, we'll have the false. There's just going to be a short little description of the article, an image, and the title. And if the user wants to read more, they can just go visit the source with our button, and that's it for frontend.
For the backend implementation, what we did was, we started with using Django and also the REST framework in order to speed up development time and also make the system a lot more modularized. This acts as an interface between the front end and the machine learning model. And because of the REST framework design, it ensures that fellow programmers will be able to use our AI model for processing without having to create their own. And this is opened under API, the API endpoint for a backend. As a result of that, this offers increased modularity even for future applications. And finally, our API also allows for task scheduling that can routinely get daily news for the server. So the request time is quick and making the server a lot more performant. For the web scraper, we use a library for Python called NewsPlease that extracts text information for each news article from HTML. This allows user to insert their URLs and have pre-filled forms of titles and bodies of each news article. And also, because of this web scraper, we can also look at news sites through their RSS feeds and have the scraped URLs sent to the NewsPlease to get predictions. And in the database, we use SQLite 3, and we also use caching to store previously scraped news article. This was implemented in order to store previously scraped documents, thus boosting retrieval performance. And for qualitative data, we actually helped our retrieval time to go down from 1 minute 30 seconds to 11 seconds from start of request to the response time.
Okay, so for the machine learning part, first we need to define the problem that we want to solve. So fact checking is actually a really hard problem to scale. It's really hard to actually find the truth of a news article. So that's what we're not aiming at, finding the truth. Instead, it's a much more scalable problem is to distinguish between credible information sharing versus emotional manipulation. So there has been a lot of research on psychology that has shown that increased emotional content negatively impacts cognitive function. So fake news propagators use this. They create a space full of emotions so that the reader cannot draw their own conclusions. So the problem itself comes down to finding words or sentences that are emotionally engaging and suppress cognitive function. Bad style, such as bad spelling, limited vocabulary, or term abuse is also a safe indicator of whether an article is fake or not. This is a picture of our general model pipeline. We started with the data sets that we've collected, and we're going to talk a little bit more about them in the next slides. First, we have to split these data sets into training data and test data. We use the training data to pre-process it first using NLP techniques, natural language processing. After the data has been pre-processed, we continue to tokenize it. Then we vectorize it using two different mechanisms, bag of words or account vectorizer, and a TF-IDF vectorizer. After the data has been vectorized, we proceed to classify it. And for this, we've trained 4 supervised learning classifiers: naive Bayes, decision tree, logistic regression, and AdaBoost. We use the test data to evaluate the performance of each classifier. Then we pick the best model, and we can use this model to basically classify novel news articles based on the user input. Our final model is going to output a label, whether the news article is most likely fake or not, and the probability or confidence value of truth.
For this project, we used 2 main data sets. The first data set was first cited in a paper by Ahmed et al., which had about 45,000 examples split roughly 50-50 between fake and real examples. In this paper, the author defined fake news articles as those being defined by serious fabrications that were not in mainstream media, large-scale hoaxes, or things intended to almost be humorous. The second data set we used was cited in an article by the engineer named Aaron Edel. His data set had 51,000 examples, which were again roughly split 50-50 between fake and real. Instead of attempting to define fake articles, he took articles which he knew were entirely true, such as by the Associated Press, and then labeled everything else as fake. When we're working with language data like this, there are several natural language processing techniques that you can use and that we did use to reduce noise in data. The first step is text cleaning. This involves taking in a body of text and removing special characters, non-English words, numbers, and other things of this nature. The next step is tokenization, which is splitting up a document into each individual word. So if we had a full document, just splitting it up into a list of the words involved. We then use lemmatization, which is removing each word to its base by pruning any prefixes, suffixes, or any other modifiers that might be on a word. The last step we do is stop word removal, which involves removing words from the document like I, and if, which, while extremely common, don't actually convey that much information about a document.
Okay, so the next step is to do vectorization on the preprocessed data. Vectorization just means mapping words to a vector of real numbers, which are used to find word predictions and similarities. We use 2 types of vectorizers for our project, which are implemented using the Python library scikit-learn. The first one is a count vectorizer, or a bag of words. This vectorizer just basically counts the number of times a token shows up in a corpora, in the entire data set, and uses those frequencies as a weight for each token. The second kind of vectorizer is called the TF-IDF. This vectorizer instead uses the weights assigned to each token depends on both the frequency of each token in a document and in the entire corpora. So here's a more detailed explanation of how TF-IDF vectorizer works. This is just going to be the product of the TF and the IDF. TF stands for term frequency. This basically measures how frequently a term occurs in a document, and this value is normalized by the length of the document. So you can see the formula on the left that the TF of a term of a token T is just going to be the frequency of that token in the document divided by the total number of terms in the document. The second part is the IDF, or inverse document frequency. This one measures how important a term is by weighing down frequent terms and scaling up rare ones. So the definition for the IDF is going to be the natural log of the total number of documents we have divided by the total number of documents with a term or token T in it. The next step after we've vectorized the data, that is, we've transformed those words into numbers, we use this TF-IDF matrix of weights as input to our classifiers. For this one, we've also used the Python library scikit-learn to train 4 different classifiers. And in the table, you can see each classifier with the parameters we've used for each. So the first one is logistic regression. We've used the L2 norm as the loss function for that. We've used the LBFGS solver, and we've run 100 epochs for logistic regression. The second one is naive Bayes, and for this one, we've used Laplace smoothing. The next one is decision tree using Gini impurity as the split criterion. And the final classifier is data boost, which is an example with a base estimator of a decision tree with a max depth of 1.
For each of these classifiers, we used a technique called 5-fold cross-validation. The way this works is the data set is split into 5 even folds, and then iteratively each fold is predicted by training on the other 4. This way, we ensure that the examples that we set aside for testing weren't some flukes or anything like that, and then we average the metrics across all 5 trials. For each of these, we output the accuracy, which is how many we predicted correct out of the total number of examples, the precision, which is the true positive rate, the recall, which is the false negative rate, and also the area under the receiving operator characteristic curve. Looking at the first data set, the best classifier was the AdaBoost classifier, which predicted accurately with an accuracy of 0.996, high above our expectations. For the second data set, the logistic regression classifier was actually the best, with an accuracy of 0.92. And finally, when we combined the data sets and trained on that, the logistic regression classifier was again the best, with an accuracy of 0.973. Here, visually, you can see some plots of the accuracies of the different classifiers across the different data sets. In data set 1, the accuracies were quite high across the board. And for data set 2, while lower, they were still higher than we had anticipated them being. For the combined data set, we see overall good performance across the board.
We also perform a statistical assessment of differences to determine whether the performance of our algorithms, whether each classifier is statistically significantly different or not. For this, we used an R library called scmamp to produce a critical difference diagram using the accuracy values gathered using 5-fold cross-validation from datasets 1, 2, and the combined datasets. The Friedman test is used to determine whether the null hypothesis that 2 algorithms are similar should be rejected or not. Getting a significant result from the Friedman test means that we have to perform a post-hoc test, like the Nemanji test, to determine which algorithms are actually different. A critical difference diagram can be useful to visualize the results. Those algorithms that are not joined by a line are statistically different. So when we set the significance level to 5% on the left, there is a line joining all of our algorithms in our critical difference diagram. This means that we cannot reject the null hypothesis that all algorithms perform equally, or in other words, there is not enough evidence to determine that any algorithm is significantly different from any other. We need to set our difference level alpha as high as 31% to obtain a significant difference between logistic regression, or LR, and naive Bayes, or NB, as shown in the diagram on the right. This means that we are only 69% confident that these 2 algorithms are significantly different.
So in summary, our website makes fake news detection easy for anybody to use. The API ensures that other programmers have access to our tools, and it allows for future expansions. We learned that NLP and vectorization techniques are useful to really understand the structure of human language, and allows us to analyze different aspects related to fake news prediction, such as syntax and semantics. Finally, we discovered that logistic regression and AdaBoost generalize the best among our classifiers, and they achieve around a 97% cross-validation accuracy on our tests. For our demo, you can go to newsneuralizer.herokuapp.com, and we have it up right now. If we go to our website, you can see the forms. We have the URL scraper form right here, the manual input form here, and then our news feed, where you can just continually search through and see what our learning models thought of today's news. So let's put our scraper to the test. We put in a URL and we wait. Over here, it's shown our result. So it's got the title, Chauvin trial, Minneapolis. A lot of cities increase their security, and then the body that it scrapes, all this information is pretty good. So we'll go ahead and ask it to analyze our data. It believes that the article was written very well. It's true, 100%. And here's, the rest of the article. If we further scroll down, if we want to read more about this article, we can just visit the source, and it will bring us directly there. That's it for our presentation. Thank you for watching.